Hello guys and hello everyone and welcome to day 2 of limits. Today's going to be a little more in-depth and maybe not as familiar as you guys may have thought the lesson 1 was. So a theorem, if we want to be exact of what a theorem is a statement that can be proved using some idea of math. And so that's what we're going to look at here for limits. We're going to look at a few theorems, look at how they are used across today's lesson, and then use them to actually solve some problems. So, the first theorem, and I should state that this is probably a poor way to write it. We should write maybe a variable there. So we could put a q. Of course, we're not going to work with my pen. We could put a q there if we wanted to. So the limit as x approaches q of c. Now what is c? So we got to think back to last lesson. Last lesson we said the limit as x approaches a certain number of f of x. So we're saying that's f of x. Well, what is f of x? Another way to write it is y. And so we're saying that y equals c. So let's think about that. Y equals c. What does that look like on a graph? Well, y equals 6. That's a straight line. So Q is a straight line. And so we can talk about that being Q right there. And so the limit as x approaches, nope, not correct, guys. Back up there. That is C. That is the line y equals C. Q is anywhere here. Sorry, let's be correct there. Q is anywhere here. Q's any of those. And so we're looking at what is it approaching at every single one of those points. Well, it better be that value C. And so we want to say this better equal C. Anywhere. Anywhere that Q is. Any of these are Q's. It better equal C. The theorem that we're going to actually use, using words to prove it, if f of x equals C, so y equals C, and c is a real number, then for all real numbers, the limit as x approaches c, or as x approaches a number of the function c, it better equal c. So then for all real numbers, we can state that using a double barred r. Instead of having to write that all out, we could use that. So again, the limit as x approaches any number, we called it q over here, of the function c, the limit better be c because it's a straight line. And we know that the straight line never changes, and so therefore the limit better equal that line. The next theorem that we're going to use is a limit as x approaches a of the function x. So we're saying f of x equals x. We know that's another way of saying y equals x. Well, if we graph y equals x, then we know that at any value of a here, that's a, what better that y value be? Well, if y equals x, that also better be a. And if we said that this was maybe a prime, then this right there better be a prime. And so what we're trying to state with this theorem is that any value, any number that we are looking at, the x value, a value, the limit better be the y value. And so what is that y value? That y value is a. Because this is y equals x, and we know that what it's approaching, that number that we're approaching is a. So if f of x equals x, or y equals x, and a is a real number, and for all real numbers, the limit as x approaches a of x equals a. So using those two graphs, hopefully that makes some sense to you. So we're going to look at a couple rules for computing limits here. The limit of a sum is the sum of the limits. Another way of writing this is the limit as x approaches a of f of x plus the limit as x approaches a of g of x equals this limit of the sum is the sum of the limits. So we're adding the sums here, we're adding the limits here. What we get is the limit as x approaches a of f of x plus g of x. Okay? So the limit of the sums is the sum of the limits. So sum, and then we can just add those there. The difference, same idea here, you just put a subtraction sign. The product, you want to write that down, the product limit as x approaches a of f of x multiplied by the limit as x approaches a of g of x equals the limit as x approaches a, probably should have an a there, of f of x times g of x. The last part here is the limit of an nth root is the nth root of the limit. And so what is this saying? This is saying the limit as x approaches a, the square root of x, also equals the entire root, the limit as x approaches a of x. And we're going to use that in a little bit. I did skip the quotient. Of course, the quotient's exact idea is this without multiplication. Okay, so moving on. I know it took a while, but those are important. I'm going to show you a couple here and then not go in depth with these, but limit as x approaches a of f of x plus g of x. Knowing that the limit as x approaches a of f of x equals 2, and the limit as x approaches a of g of x equals negative 5, we can't just say 2 plus negative 5 here. What we need to do is write it out so we can use this. So we can write this out as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. We know that using the summation rule. Now we know that this entire thing is 2 plus that entire thing, negative 5. Now we can say the limit of that equals negative 3. And again, how would I write this out? Not like that. This is very poorly done by me. What I would have most likely done is said that that equals that, which then equals 2 minus 5, which equals negative 3. Much better way of writing than what I was doing. For this one, notice that the 2 is a constant, the 2 and the 3. So what we're going to do here is we can write it as 2 multiplied by the limit as x approaches a of f of x minus 3 times the limit as x approaches a of g of x. And then we can go here equals, man, I'm just as bad as you guys, I forget the equal sign, 2 times 2 minus 3 times negative 5. And we're going to get 4 plus 15. It's an equal sign, 19. With this one, make sure that you realize that we can rewrite that. So the limit as x approaches a of f of x. And so we know it's the square root of 2. This one, you don't need to write it out completely, but we can do 4. I'll write it out anyways. It's good for us to see. G of x divided by the limit as x approaches a of f of x, all squared. Okay? And we're going to get 4 times negative 5 over 2 squared. Notice that the 4 and 2 squared cancel. And so therefore we're just left with negative 5. Moving on. I'm going to kind of rush through this. Apologize for that. This is important. Notice that the limits of a function. Now these are just actual functions here. This is a quadratic. What do we know about quadratics? Quadratics are continuous and there's no breaks in them. Therefore the limit better be that actual value that we plug into. So you're going to plug in and stop if you get the answer. That only works, this number 1 works, is if it's a polynomial. So we can basically state that that's 5 squared minus 4 times 5 plus 3. And we know it's 25 minus 20, which is 5, plus 3, which is 8. Done. You don't even need, the limit goes away once you plug in, just so you know that. The limit goes away, the limit symbol goes away once you plug in because you're evaluating the limit when it's gone then. With this one, if you plugged in 4, you're going to get some number divided by 0. This has an asymptote, right? It's going to look something, I'm guessing here at 4, it's probably going to look something like this. Okay, asymptote would be at 5. So take away the drawing, but you're going to get an asymptote here. Notice that a horizontal asymptote would be at 5. Bad drawing on my end, but you get the idea. You can't just plug in. So when we do this, we are going to say that the limit does not exist because the limit as x approaches 4 from the left does not equal the limit as x approaches 4 from the right, because we're going to get negative infinity and positive infinity not the same. So make sure you understand that. That's where you get 3. If you get 0 over 0, you need to simplify. So, example here, if I plugged in 2, I'm going to get 0 over 0. I'm going to get 4 minus 4 over 2 minus 2. 0 over 0. So what do I need to do? I need to factor it out. This is a limit as x approaches 2. You cannot lose that sign. That's what that equals. You can cancel those out, and therefore you're going to get the limit as x approaches 2 of x plus 2. And then I'm going to evaluate, now that I have a polynomial, or in this case just a linear function, 2 plus 2, which equals 4. Notice when the limit sign goes away. Same idea here. You can factor that. I'm going to skip that one for now because we're going to run out of time on the video. In this case, note that you're looking at solely from the right. If you graphed it, you have an asymptote at 4. I'm pretty sure 5, 1, yep. It's going to look like this. And therefore, from the right, as I go to 4, I'm going to infinity. So I'm going to get infinity right there. With this one, you're going to need to multiply by its conjugate. So I'm going to pause the video. I'm going to do it out, and then you can see what I do just to save time. So what I've done here is multiplied by the conjugate. I did not, please, please, please do not distribute this x to both of them. You're going to see why, but just remember, never distribute unless it's the one you're actually multiplying the conjugate by. So x parentheses the square root of x plus 1 plus 1. When you multiply the conjugate, you're always going to get a plus b times a minus b. When that happens, you're always left with a squared minus b squared. So what you notice here is a, this is your a, that's your b. So what is a squared? Well, what's the square root of x plus 1 squared? X plus 1. The 1 squared is 1, and then you have the subtraction of that. So you're going to get x plus 1 minus 1. Not always, but most of the time, we are going to be able to get rid of that sign. The limit as x approaches 0 of, again, do not distribute that. What's 1 minus 1? Just x. Notice here that you can cancel the x's out, and now you can evaluate it. That's the 0 plus 1 plus 1. And that's 2. I evaluated. After the x is canceled out, now I can plug in. So notice that if you had plugged in before, you would have gotten 0 over 0. And that doesn't work, so we have to simplify it. This is how we simplify something that cannot be factored. We multiply by its conjugate. Okay? Hope that makes sense. If it doesn't, go back in the next previous page and read those 3 steps. The last example here, g of x, is a piecewise function. You have 2 separate functions here and here defined by the domain of x is less than 4, x is greater than 4. What I like to do on these is draw them out. So we have x squared starting at 4. So we're going to be at 16 here. Okay, and it's basically going to come down here and way back up with an arrow. And 2x minus 6, you're going to draw that at 4. You're going to start at 2. Okay, so we basically have there at 2. And it's increasing with a slope of 2. So, looking quickly, 20 seconds to go. From the right, I'm at 2. From the left, I'm at 16. And what is my limit? Well, those do not equal each other, so therefore, it does not exist. Hope that helped. If it didn't, ask me questions in class. Bye.